In the second part of this lecture, we're going to review cross-sectional and ecological studies. A cross-sectional study examines the relationship between diseases or any other health-related condition and other variables of interest that exist in a defined population at one particular time. The hallmark of cross-sectional studies is that exposure and disease are evaluated at a single point in time, and because of this, these studies are also known as prevalence studies. We have many examples of these studies in Canada assessing the prevalence of health conditions and risk factors at the same point in time to provide a snapshot of a health problem and risk factors simultaneously in a defined population. For example, we have the Health Canada and Statistics Canada surveys, such as the Canadian Community Health Survey, the Canadian Health Measures Survey. We also have the Aboriginal Peoples surveys, and in Alberta, we have, for example, the Real Kids Alberta, which is an initiative between the School of Public Health at the U of A and Alberta Health to provide some measurable health outcomes for children in Alberta. There are several steps in conducting a cross-sectional study. First, you formulate your research question, then you define the target population and decide on the data collection methods that will be used. Then you need to select the type of sampling from the population, and this can be non-probabilistic or probabilistic. Then you need to measure the exposure and outcome of interest, and then analyze the collected data. Typically, the measure of association reported in cross-sectional studies are odds ratios. Cross-sectional studies are the most appropriate method to assess prevalence of common outcomes and provide information on the burden of disease and services needs. Cross-sectional studies cannot determine whether exposure precedes disease, so they are good to assess associations but not causality. Cross-sectional studies are also not very useful for rare conditions or for quickly emerging diseases or outbreaks, and this is because people who die quickly or recover quickly are less likely to be identified and therefore not being captured in the study. There are many tools to assess the quality of cross-sectional studies, and I'm bringing you now a checklist developed at the Joanna Briggs Institute in Australia. This checklist assesses quality in relationship with different domains, such as representativeness of the sample, the adequacy of the sample size, the setting if it was described with sufficient detail, and some other factors related with data collection and analysis. Ecological studies, also called aggregate studies, evaluate an association using entire groups rather than the individual as the unit of analysis. In epidemiological terms, a group is considered a collection of two or more people, and it can be anything from a household, school, or village to a nation or a group of nations. In an ecological study, you compare the exposure status and the outcome status of the groups, and for each group, the exposure and the outcomes are measured for the group as a whole. You can identify ecological studies in the literature by the fact that they use the average exposure for a population and population level outcome data. Now, here we can see some aggregate level data from a study by Dole and Hill in the 50s about cigarette consumption and lung cancer mortality in 11 European countries. The independent variable here is per capita cigarette consumption in each region in 1930, and the dependent variable is lung cancer mortality rate per 1,000 in the region in 1950. We can see in this ecological study a strong positive association between rates of cancer mortality and per capita cigarette consumption. Let's take a look at another example. In this study, the authors linked country-level agricultural census data and cancer incidence data in registries for children diagnosed between 2004 and 2008 in 6 states in the Midwest of the US. Crop density in the states was estimated, And the state level analysis revealed additional positive associations for total leukemia and central nervous system tumors in the children, and differences among the states for several crop density rates. Another example is an ecologic analysis conducted to explore the association between air pollution in China during April and May 2003 and SARS case fatality. A linear model was fitted to the data for 5 regions in China with 100 deaths by SARS or more. And the authors found a positive association between air pollution and SARS case fatality in the Chinese population by using publicly accessible data on SARS statistics and air pollution indices. There are three different types of ecologic measures. Aggregate measures, which are summaries of observation that come from individuals in each group, for example, a proportion of smokers or median family income. Environmental measures are physical characteristics of the place in which members of each group live or work, and each environmental measure has an analog at the individual level. And these individual exposures or doses usually vary among individuals in each group, though they might remain unmeasured. Global measures are attributes of groups or places for which there is no distinct analog at the individual level, and examples would be level of social organization or the existence of a specific law. With this, we can see that there is a difference between making inferences when data is collected at the individual level or when data is collected at an aggregate level. And here's an example. In this study, the authors assessed whether individual motorcyclists wearing helmets will have a lower risk of mortality. Here, we're talking about effects of individual risks. On the other hand, in this study, the authors want to know where the rates of motorcycle-related mortality of riders vary across different states that have different helmets law. In this case, data and inferences are about the effects on group rates. Some ecological studies compare groups from different geographic regions, while others compare groups at different points in time. These are also called time trend studies. We will briefly look at each of these study designs now. In a descriptive multigroup ecological study, we, for example, might compare rates of an outcome among many geographical groups during the same time period. In this case, we do not start with a specific hypothesis, but we can search for spatial patterns of the distribution of an outcome to generate hypotheses about the possible causes of the outcome under study. In analytical multi-group ecologic studies, we set out in advance a specific hypothesis and we look for an association between the level of exposure in each group and the rate of the outcome in each group using many groups. This is the most common ecological study design. In a descriptive trend ecological study, we compare rates of an outcome over time in one geographically defined population. We search for temporal patterns that might suggest more specific etiological hypotheses. So this is very similar to the multi-group ecological study. However, the groups are not different geographical groups, but it's the same population at different periods of time. In analytical time trend ecologic studies, we set out a specific hypothesis and then we look for an association between a change in group exposure and a change in the rate of an outcome in one geographically defined population. So, similar to the analytic multigroup ecological study, however, the groups are not different geographic groups, but it's the same population at different points in time. Several practical advantages make ecological studies especially appealing for undertaking different types of epidemiological research. They are not expensive and are very useful for the generation of hypotheses at a populational level. Despite these advantages, ecological studies have some problems of interpretation when making inferences at the individual level. So the correlation at the group level might be valid in an ecological study, but the correlation might be invalid as a statement for individual causal effects. So we often require both ecological and individual level data to make valid inferences. One of the example of this problem is what we've called is known as the ecological fallacy, also known as ecological bias or cross-level bias. Ecological fallacy is a condition in which you draw an inference about an individual on the basis of trends observed in a group to which he or she belongs. You would assume, by making the wrong assumption, that as the variables correlate in an ecological level, they would do the same on an individual level. So inferences using group level data might not always be correct at the individual level. So for example, associations that found at a country level data might not correlate with associations that exist at the individual or neighborhood level. Let's suppose that in a class of 50 students, the average IQ level is high. However, if you pick a random student, it doesn't necessarily mean that he or she will have a high level of IQ too. Such an assumption is an example of ecological fallacy. It might happen that there are a few students who have an exceptionally high IQ, and in that case, although many students have a very poor IQ level, you might end up with the misconception that just because a student belongs to that particular class, he or she has a good IQ level too. Let's see another example of an ecological fallacy. So, states in the United States with proportionally more immigrants have proportionally more households with income above 100K. Therefore, you would be tempted to say that immigrants are more likely than non-immigrants to have households incomes above 100K. Actually, the relationship between income and being an immigrant at the individual level is the opposite. At the individual level, 77.9% of immigrants in the United States have a household income below 100K. Deducing from the first chart that immigrants are more likely to be well off is committing the ecological fallacy, which is attributing qualities at the individual level because of a relationship at the group level. In this lecture, we have reviewed some basic observational study designs in epidemiology. The next week, we will dig into other types of studies such as case control and cohort studies. In the meantime, remember to complete Trivia 4 for this week, participate in the forum, and complete the assignment, which is a short critical appraisal of an article that uses one of the epidemiological designs that we just reviewed this week. See you soon.